I'd like to get started. So, there's a lot of people in class today. That's great. Thank you for attending ECS 173, everybody. Last Friday there were about 5 or 6 people, and I thought that was sort of going to be the steady state attendance, but there must have been a midterm or something. Okay, so today we're going to talk about invariants, and what we're going to do here is, first of all, rewind a little bit. Sorry, I have a cold. And recall the several lectures where we talked about finding matches between little image patches or regions in one image and regions in another image. And I told you about the several different applications where this is kind of a cornerstone part of that application. And recall further that if you are given images that you want to find correspondences between, what I did is I gave you a 3-step recipe for how to find correspondences that applies to a number of different algorithms that you might actually use in practice. The first step is to take your image patches of interest and represent them as a vector of numbers, where you simply, what's called rasterize. You take all of the intensities of all the pixels and represent them as a vector. The second thing you do is basically convert that vector of numbers into another vector of numbers called a feature vector. And your feature vector lives in what I call the feature space. And that conversion from the original set of image pixels to the feature vector could have one or another different favorable properties to it. It could reduce the dimensionality so that you basically have less data that you have to deal with while you are trying to find matches. It could be invariant, which is to say that if you transform the image patch in a number of different ways, you still get the same feature vector out of it, and so on. And then, once you have converted your image patches into feature vectors, then the third step is simply classification, which is to say, given a novel a novel feature vector, look around it in the feature space and see if you see similar ones to it. And in the object detection type of case, basically you would have feature vectors corresponding to, for example, faces or cars or whatever your category of interest is, and feature vectors corresponding to all the other stuff in the world. And given a new one of these image patches, you would convert it to a feature vector and see if the feature vectors in its neighborhood looked like they were mostly cars or mostly other stuff. And in other examples, for example, where you have tracking from one image to the next, and you want to find a match between this patch in this image and this patch in the next image, you would have feature vectors corresponding to the patches in this image, feature vectors corresponding to the patches in this image, and you would use the features to tell you possible matches for that, just by looking in the feature space in the vicinity of it. Now, let's look at that second step, which was to generate a feature vector for every one of our image patches. And I gave you a couple of different choices there for what you might do. One of them was called, to use what's called an invariant feature function, which is to say you have your feature function, f, which is the thing that maps your image patches to feature vectors. And what I told you is that this feature function is invariant to a set of transformations if, no matter how you transform the image patch with respect to those transformations, you always get the same feature vector out. So if a feature function is invariant to rotations, which is to say you rotate the guy's head around in the image patch, if it's invariant to rotations, then no matter how you rotate that person's face, you're always going to get the same feature vector out of it. And there are other examples. If it's invariant to lighting, then if you just make the entire face brighter, 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 you always get the same feature vector out. So a little bit more formally, we usually think about a set or a class of transformations where each element in the set is referred to by a capital T. And that can be the set of rotations, for example, or the set of scalings, or the set of translations. And this thing is a function that takes an initial image patch, call it V, and transforms it to another image patch. So it's the domain of T is the set of is image patches, and the range of it is image patches as well. And all I'm saying here is that f is invariant to the class of transformations T if f of v equals f of t of v for all possible t's. So we're going to talk about this notion of invariant feature functions in more detail today and talk about specific implementations of this. Does the setting of this make sense to everybody? Okay, good. Now, with respect to these invariant feature functions, there are basically two different strategies that are taken in the literature. One of them is what's called rectification, which you can simply think about it in your head as the process of undoing the transformation T. So the notion here is that, let's go back to the example of rotation. The idea is that there's some canonical rotation of that person's face. So you can think about this as the identity transformation. It's that there's a canonical orientation of the face, for example, straight up and down, and that what you want to do is think of all possible transformations or all possible rotations of that image patch as being rotations from this canonical orientation to some other orientation. Okay, so what rectification does is it undoes that rotation so that it snaps all the faces back to straight up and down. So it tries to undo the transformation with respect to some canonical or identity transformation. And here's an example of that. Imagine that you have two versions of the same image patch, this one and that one, and that instead of the canonical orientation of the cornflake box being straight up and down so that you can read the word cornflakes, let's just say that there is a canonical orientation of the cornflake box so that the words cornflakes are pointed in that direction. And let's say you have a procedure or a black box, a purple box really, that rectifies the image patches so that no matter what the cornflake box looks like in terms of what its orientation is going in, this rectification box fixes it so that it's oriented in this direction. And similarly here, you have another input image, and this rectification box does that thing again, where no matter what the initial orientation of the cornflake box was here, it reorients it so the words cornflake are pointed in that direction. And furthermore, this rectification box is even snazzier than what I've been describing already because it's rescaling the one at the top so it's the same size as the one on the bottom. So it's taking this smaller straight up and down patch of cornflake box and reorienting it and rescaling it so that this guy is basically exactly the same as that guy. So now it should be clear that once you do this rectification thing, then your feature function can really be anything at all, and you will always get the same feature vectors. Assuming, that is, that your feature function is something rational that always gives you the same feature vector if you give it the same input over and over again. So this is just another way of saying that if you take your initial image patches and you remove all the differences between them so that they're basically identical to each other, then you will always get the same features out no matter what the feature function is. Does that make sense? So this is basically taking this invariant problem and converting it into a problem of removing all the variability between image patches. And again, with the notion of there being a sort of a canonical transformation or an identity transformation with respect to your set of image patches of a particular object. Yeah, use the mic, please.
I have a question. So, doesn't this raise kind of a chicken and the egg problem because we have to detect that there's a rotation, fix it, and then presumably then we're going to try and detection, right?
Right.
So how do we recognize something's rotated if we don't know what it is yet?
Well, what you have to do is start out by assuming that there is a particular set of transformations that your objects are allowed to undergo. And so let's say we have faces. So what we would have to do is conjecture that across the space of all of our different images, I'm only ever going to see rotations and, let's say, scalings of a canonical face. if anything else happens, then this is kind of, it blows your whole detection scheme out of the water. So if the images, let's see, what's a good example? If the faces are rotated out of the plane like this so that they go to half profile, forget it, this will not work. So that's the key kind of, I try to make it clear when there's a free lunch, which is never, and what you have to pay for to get your lunch. It's kind of stretching that analogy, but anyway, for this, you basically have to start by making an assumption about what possible transformations T your image patches could undergo. And if you violate those assumptions, then all bets are really off. Any other questions? So the other strategy is a little bit more straightforward. So here we actually construct this feature function f de novo, or from scratch, such that it is invariant to these transformations without actually having us do this pre-processing step. That's another way to think about rectification. It's basically a pre-processing filter for your image patches to make the feature vector part really easy. And this part actually puts the onus on the feature vector, the feature function, to make it do the right thing by having the output of it be invariant to your set of transformations. Anyway. Now, there are basically two different scenarios in which we would use the notion of an invariant. And they correspond to the two different scenarios I told you about when we're doing object detection. So if you remember, the two ideas in object detection for how you would actually detect an object in an image in practice is that the first one is called dense matching, in which you would take a box, and for every you would scan through the image, and for every location in the image you would say, well, is the cornflake box here? No. Was it here? No. Is it here? No. Is it here? No. And so on. Sparse matching is the opposite of that, where you try to use some kind of a pre-existing mechanism for telling you what parts of the image are interesting, salient, any of those kind of vague terms, and then you would just look for matches for the cornflake box at those isolated locations. So what you can do in this, if you take this sparse matching approach, what you can do is actually try to find regions in the image that are both interesting and invariant to a set of transformations at the same time. So what I mean by that is that you can try to identify, let's say, for example, a region, which is to say a rectangle of image pixels in the one image that is invariant to rotations. So in other words, no matter how that part of the cornflake box is rotated, you'll always get the same set of pixels. And in fact, what you can usually do with these sort of interesting region approaches is actually rectify them as well. So your pre-processing step that tells you where the interesting regions are in the image would not only tell you that the green box here is interesting and that the green box here is interesting, but it will suggest to you a way to rotate both of them so that you end up in a canonical orientation. Does that idea make sense? So, in fact, there's a whole, you can front load your detection mechanism so that it does this kind of generally interesting and transformation invariant region detection before you even suggest to it what the features of it are. Now for dense matching, what we basically do is we apply rectification or invariant feature functions everywhere in all images and possibly at multiple scales. So we have the same sort of dynamic as earlier, where with sparse matching you're making this big leap into, you have to believe basically that your invariant and interesting image patch detector is doing everything that it needs to be doing, and that it's actually going to find interesting regions on your cornflake box of interest. And if not, you're in trouble and you're not going to detect the thing, period. Dense matching takes a lot more time because you are doing a lot of computation on each one of these patches, even though they don't have any interesting content in them, but you'll never miss the cornflake box. So it's the same thing over and over again about dense versus sparse matching. So what I told you is that we try to construct a feature function that is invariant to some set of transformations T. So let's talk about what that set of transformations T could be. So the first set, that is probably the most prominent, is what's called geometric transformations. So what T does is it basically maps coordinates to coordinates. Or in other words, it maps pixel locations to pixel locations. Or if you want, it maps xy to xy. And what you can do to visualize what a particular set of geometric transformations does is by starting with an initial square that looks like this and seeing what kinds of outputs you can get from that class of transformations. So the rotations are what you are all familiar with, that you can basically just take this thing and rotate it to some degree, and it's parameterized by the degree to which you rotate it. If you add to that the idea that you can not just rotate, but that you can uniformly scale the square, then you end up with what's called the set of similarity transformations. So when I say uniform scaling, what I mean is that both the vertical leg of the box grows, well, basically the vertical part grows by the same amount that the horizontal part does. So if this gets twice as long, that gets twice as long too. And the set of these, I'm not sure why this is exactly, but the set of rotations and uniform scalings is called the class of similarity transformations. If you then add shearing and anisotropic scaling basically means that you can make the vertical part arbitrarily long, and you're not constrained to make the horizontal part as long. You can make it, basically turn the rectangle or the square into a long, elongated rectangle in either direction. If you add the ability to do that, and you add this thing called shearing, which basically turns rectangles into parallelograms, then you end up with the set of what's called affine transformations. So this comes up a lot, where someone will propose to you a new region detection, sparse region detection technique, and they'll say, this is great because it's affine invariant, or it's invariant to the set of similarity transformations. Now you know what that means. But basically, if you were to take the image of the cornflake box from straight on, this big, and you were to move back and kind of tilt the camera so that it ended up looking like this, you can use an affine invariant region detector to basically detect that that and that were images of the same thing and undo this shearing thing. Another set of geometric transformations has to do with camera projection. We're not going to talk about this in this class because it's hugely complicated. But basically what happens is that there are objects in the 3D world that you take a photograph of. And any particular object has a set of points on it that is defined by a set of 3D coordinates, xyz, xyz, xyz. Well, getting from that 3D position in the world to a 2D position on the camera plane of your camera requires a process called projection that can go from arbitrarily simple in how you model it to arbitrarily complicated if you consider all of the really complex things that go on inside the optics of your camera. And so one goal could be to make feature functions that are invariant to how that projection process happens, or over a range of projection parameters. But we're not going to talk about this, and you won't really be responsible for it on the exam. Now, outside of the set of geometric transformations, you can imagine having, and this is kind of the example that I referred to earlier, you can imagine wanting to have a feature function that is invariant to uniform changes in illumination. So if you simply take a photograph of my face and make every pixel twice as bright, then it would be nice if your feature function didn't care about the fact that all of the pixels got twice as bright because it's imaging the same thing. And so you could potentially say that your detection scheme is invariant to changes in illumination if it always detects the face regardless of whether it's brighter or darker. So, so for the geometric case, both rectification and invariant feature functions are trying to worry about transformations T that modify the positions of pixels or other geometric primitives that are extracted from it, such as corners or edges and so on. And so they'll either formulate T as a transformation of individual xy or xyz coordinates, or as a transformation of geometric primitives such as points or edges. So what I'm saying is that basically you can either start by thinking about this transformation T as modifying the positions of all points in the interior of your image patch, or you can start by assuming that you extract geometric primitives such as edges and corners from it and see how to undo the transformations to those geometric primitives. And so, for example, you could say, well, what I want to do is have a feature function that is invariant to the rotation of this particular triple of points that makes this corner. Excuse me. Or you could say, I want to have an invariant feature function that is invariant to the angle that is made by those three points, by that triple of points. Now, you might consider what you have learned in geometry class, probably when you were in maybe 10th or 11th grade, about different geometric primitives. They might not have called it this, but you probably spent a lot of time doing, or actually I did, I don't know if you did, doing proofs about angles and distances and areas of things. So proving that if you have a triangle over here and another one that's in a particular configuration with respect to it, that the angle of this thing is the same as the angle of that thing. And so if you go back to those really basic geometric primitives such as angles and distances and areas, and you go through the math of transforming them using some of the transformations we've been talking about, you'll find that some of these are automatically invariant to some of those. So, for example, angles, and this you shouldn't even have to go to the math to do it. If you think of the angle between my thumb and my hand and my index finger here, and I rotate it, I haven't changed that angle at all. And I can't make my hands bigger and smaller, but you can imagine if my fingers get longer and shorter, then this angle doesn't really change at all either. Similarly, let's see, the distance between my two fingers stays the same if I rotate my hands. And similarly, if you take a rectangle, this happens with cardboard boxes when you're moving them a lot, right? Where you start out with a cardboard box that has right angles, and you can shear it so that it turns into a parallelogram-looking thing. You didn't actually change the length of any of the sides of the box, did you? So that's another way of saying that distances are preserved by shearing, which is this tilt, being able to tilt a box and turn it into a parallelogram. Now that shearing took all my 90-degree angles of my cardboard box and turned them into not 90-degree angles anymore. So shearing does not preserve angles. It's another way of saying that. And finally, let's see, areas. So if you were to take the surface area of, let's see, the bottom of your cardboard box before you cut it out and collapse it, and you rotate it, well, you haven't changed the area of that thing. And if you need a flexible cardboard box to do this, but you could imagine tilting the cardboard box in one direction or the other, and you haven't actually changed the amount of cardboard that's on the bottom of it. So shearing preserves area. So if you keep these things in mind, then you can imagine having a feature function that is very, very simple. So let's say that I am able to describe my object that I am imaging in my image patch, like my cornflake box, in terms of a set of discriminating geometric primitives. So in other words, there's an angle between, first of all, there are edges that are easy to detect. And I kind of show that here. So imagine that I have a very distinct edge and another very distinct edge that meet on my cornflake box. And there's not a lot of other things in the image that are edgy in this way or that form an angle that's like this. And furthermore, let's say that I am only ever going to see images of the cornflake box that are rotations or scalings of some canonical one. Well, then I can use that angle as an invariant feature, because it's automatically, by dint of the fact that it's an angle, going to be invariant to that class of rotations and scalings. So you can do very simple things like calculate angles and distances and areas of things and automatically get some invariant properties out of it. So going from very, very simple to very, very complicated, you can take derivative of Gaussian functions and convolve the image with them and take features of those, and they will be rotationally invariant. So this is a set of features that doesn't have to do with simple geometry, but it has to do more with intensity-related features. So let's go over this in a little bit more detail. And I think I lose people every time I present this, and I haven't quite figured out how to do it in a simple way, but nonetheless, I is going to be our image of interest. So that's I. And G is a Gaussian blurring filter. So this top thing is just convolving the image with a Gaussian. And the sigma simply means the standard deviation of the Gaussian. So higher number here means that the thing is wider, and smaller number means that it's thinner. The subscript, G sub x, can everybody see the subscripts here? Good. This is the derivative of the Gaussian with respect to the x direction, with respect to the y direction. And if you see two subscripts, then that's the second derivative of Gaussian with respect to the x direction, with respect to the x and then the y direction. So it's the cross derivative, and with respect to the y direction again. And again, with each one of these, we're convolving the image with the thing on the right. So we talked about this on maybe the third or so class, about how convolving the image with one of these, a first derivative of Gaussian, gets you edge detection and smoothing at the same time, right? And that if you want to find peaks of this thing, it's equivalent to finding zero crossings of these guys, right? Because if you find the peak of the first derivative, it's where the second derivative goes to 0, right? And let's just say that, just to keep the notation compact, that I refer to this thing by L, this thing by L sub x, L sub y, and so on. And I'm not sure why the letter L. I wish I could tell you what the L actually, why it's L and not Q, but I don't know. Now, you have to take it on faith, because I don't show the proof here, but there are a set of functions that are just basically linear and multiplicative combinations of these L's that are invariant to rotations. So this thing, it should be clear, is invariant to rotation, because if you rotate that original Gaussian, then you haven't changed it in any way. Similarly, if you take these linear combinations of the first derivatives, the first and second derivatives, and so on, those things are invariant to image rotation. The thing that fascinates me is that anybody figured this out in the first place, because it's not clear to me why you would bother to even investigate this, but it's true. So you can actually take just first and second derivatives of your image, and I think it keeps going with third and fourth derivatives as well, but you can use these to construct a feature vector which is automatically invariant to rotation. It turns out that that's the only thing it's invariant to, though. So if you want a feature function that is invariant to rotation and something else like scaling, sorry, you have to first rectify your image patches so that all variability in shearing and scaling and whatever else you're interested in go away. This just gives you a sense of how to get a feature function that is invariant without first rectifying. So there's no pre-processing step that first undoes the rotation and then calculates something from the patch. This just takes the patch, the image patch as it starts out, does a bunch of calculations on it, and then ends up with something that's invariant. Okay? Okay, so before I talk about this thing, are there any questions about administrative type items. The homework is due this Friday at 11:59:59, right? My office hours are after this. Everyone got the memo that Jing's office hours are now in the CSIF, one of the CSIF TA rooms on Wednesdays. And Jing, anything else? Okay. Yeah.
What's the room number for your office hours? What's the room number for your office hours again?
It's 1037 Academic Surge. So it's just 2 buildings that away. Okay, well, if there's no other, excuse me, my gosh. If there are no other administrative type of questions, then we'll go on. We'll keep talking about invariants for a little while longer. Now, let's say that what we really want is a set of image features or a feature vector that is invariant to the set of affine transformations. And let's say, furthermore, that we are able to consistently and robustly identify a set of 3 different points, which I'll call P1, P2, and P3. Or actually, sorry, a set of 4 points, P1, P2, P3, and this guy, in all images of our object. So let's say that for the cornflake box, there are 4 particular locations on the cornflake box that are distinctive and that are easy to detect over and over and over again. Then what we can do is basically construct what amounts to a coordinate frame using P1 as the origin, P2 as something like the x-axis, P3 as something like the y-axis, and make a coordinate frame out of these 3 and measure the coordinates of that 4th point with respect to this coordinate frame. So this is immediately probably going to seem kind of strange to a lot of you, because most of the time when we talk about coordinates, we're talking about the x and y coordinates in a Euclidean space, which is to say it's the usual thing where there's a right angle between the x-axis and the y-axis. So the x-axis is perfectly horizontal and the y-axis is perfectly vertical. It turns out that that is arbitrary. It's widespread and it's a convention, but it's arbitrary. There's no a priori reason really why the angle between the x-axis and the y-axis has to be 90 degrees, and in fact it doesn't. What you can do is measure, simply put, the perpendicular distance from the point to this first axis, P1, P2, and that is some distance. And it's measured in a way that I think is fairly intuitive. You kind of go along the y-axis direction to get there. And similarly, you can calculate, well, that would be its y-coordinate. And then its x, the analog of its x-coordinate would be this mu ka thing. And it's the perpendicular distance in the x-axis direction that it takes to get you from here to here. And one thing that might be helpful in order to visualize how this works is to start out with your canonical x and y-axis with grid paper on it, or with a grid of lines on it, and then tilt the y-axis, and while you're doing that, tilt the grid of points too. And if you do that, then you'll be able to see that there is a well-defined way to define the coordinates of a point with respect to a coordinate frame that is not square. So it turns out that if you are able to consistently identify P1, P2, and P3, then these coordinates, mu ka and mu kb, are invariant to the set of affine transformations. Which is to say that if you take the set of all 4 of these points and affinely transform them, which again is to say you can rotate them, you can anisotropically scale them, you can shear them, you can do any of those things, and mu ka and mu kb will always be the same, no matter what. And the proof of that is right here, which I think is fairly straightforward, and you can work through it if you would so like. So this is, and furthermore, this extends to multiple sets of 4th points. Instead of having just one 4th point that you describe the coordinates of, you can have a 5th one and a 6th one and a 7th one and an 8th one. So really what you can do is identify 3 points that are like completely important It's P1, P2, and P3, and these are the things that are going to be used to set up your coordinate system. And then all the other points can be just other points. And the coordinates of those other points really are invariant to the set of affine transformations. Does this make sense? Okay, good. So basically you can use the coordinates of those points with respect to that, you can call it an affine frame, with respect to that affine frame as a invariant feature vector per se. So I have another set of slides that come after this that, oops, let's show that again, that were made by a colleague of mine and are about this question of detecting interesting and invariant regions, which is to say finding the same region in the image no matter how that image has been scaled or how that image has been affinely transformed. And the idea here is that here I have the same curve, or I have this, you can imagine this being an image patch of this contour, and all that really happened inside of Keynote or PowerPoint is that this thing has been uniformly scaled to get that thing. So it should be clear, without doing too much thinking, that if the only thing you do to detect interesting regions is a Harris corner detector, and that you don't worry about the scaling of the, basically the size of your image patch, then this thing will appear to be one interesting region because it looks like it has a corner in it. And there will be no interesting regions over here because at that size, every local image patch looks like it doesn't have a corner in it. It just looks like it has one direction of curve in it. So you really do have to worry about the size of the image patches that you look at if you want to detect interesting regions in a scale invariant way. So if I could just switch to those slides for a moment. So yeah, this is a great set of slides that was put on the internet by a couple of colleagues of mine, which is really quite nice. So the idea here is that in order to detect the same region at multiple scales, in other words, to both detect that the thing on the right is interesting and that a big version of this is also interesting on the left, what we're going to do is consider calculating a function for each scale. So we're going to have one function and calculate it at this size for the thing on the left. Calculate the same function over the larger region that's shown there now. Calculate the same function again over a larger region. And keep going with bigger and bigger regions until we identify something that is consistent about the function as it's evaluated at this size and the function that as it's evaluated at this size. The problem is we can't just pick the same region size on the left and the right because, as you can see, on the right, the much larger region has a bunch of other stuff in it besides that one corner. So we have to actually evaluate, or we have to actually compute something over multiple scales of the images. So what I basically just told you is that for every region in the image, we consider making that region larger and larger and larger and larger, and we have some function that we're going to plot, or that we're going to calculate for each one of those region sizes. So what we can do, and this is what's called, they call it an interest function. You can call it that if you want. Originally I had it called a feature function, but that's already taken, that terminology. So we'll just call it an interest function, I, which goes from an image patch to just one number. And what's going to happen is that as we evaluate this function over different region sizes, from tiny to medium-sized to huge, it's going to plot out some set of values. And so if we imagine in our kind of hypothetical case that we evaluate it on the very large corner thing that was on the left of the previous slide, and then we evaluate it on the much smaller corner thing that was on the right, then if this interest function is doing the thing that it should do, then basically let's see, so the image patch at its smallest, well, basically what's going to happen is that this graph is going to scrunch up and shift to the right. Because really, the thing that is being imaged at the smallest scale is not even going to be on this plot. The thing that's being imaged at this scale is going to correspond to this thing over here. And basically, every scale on the thing on the right is going to correspond to a scale that's over here, just shifted over to the left a little bit because the image is larger. So if you see these two plots side by side, you can imagine one way that you could possibly detect regions that are in correspondence between the two images. And that's simply to look for peaks in this graph. You can say, I am going to report that the region corresponding to this scale is interesting, and that the region corresponding to this scale is interesting. And if you go back to those original images, this size of this region is going to be much larger because it's going to fill up the entire corner, and the region on the left is going to fill up that corner as well, but that's going to be a smaller region. As you can see, it's further to the, or wait a minute, sorry, I have that backwards. Yeah, so the region on the right, since the corner was smaller, the actual region is going to be smaller, so that they correspond to each other. So then what we're going to do at runtime is basically rectify these two image regions so that they're the same size. So that undoes the scaling that exists between the two of them. So this is kind of the general approach, is to have an interest function that basically tells you what the peak interesting scale is. And if the image region is relatively large, then hopefully the peak most interesting image region size is going to be larger. So then you can do rectification to undo that relative scaling. Now, there's a number of pitfalls with respect to this approach. What I told you is that you have to identify a peak in the interest function to identify the one most interesting scale of that region. Well, if your interest function does this with respect to, as you scale that region larger and larger, well, that's bad because it's hard to identify one consistent peak. The whole thing is peak. Similarly here, you have multiple contenders for what is the most interesting region. And there's one that is technically taller than the other two, but not by much. And the one on the right is what you really want. It's what's called unimodal. It has one maximum. And that one maximum is relatively sharp. It's not really too ambiguous as to where to put that peak. So this is really kind of the special sauce or the secret ingredient. The kind of magic part of doing this interest function is finding an interest function that has this property that it doesn't look relatively flat, so it's hard to find one peak. It doesn't have multiple peaks, it just has one. And it turns out no one has a good theory for why one particular interest function works better than others. But the ones that have been tried in practice include, for example, the Laplacian of Gaussian, which is basically the sum of second derivatives in the x and y directions. And it just turns out that if you evaluate this thing over multiple scales, you tend to get this property that there is a particular scale at which this thing peaks, and there aren't multiple peaks of it. Another thing you can do is what's called the Harris Laplacian, which is to say, at every scale, you do, in the spatial domain, at every x, y, you do Harris corner detection, and then you do this Laplacian thing with respect to scale. And then there's SIFT, which is a little bit more complicated. So, right, that's just a summary of what I just said. So that's what happens if you really care about finding interesting regions and images that are invariant with respect to scaling. So now we go on to the more complicated case where you want to be able to detect not only that this region and this region correspond to each other, but that this region and this region correspond to each other. In other words, that they are affinely transformed versions of the same thing. And again, going back to my example, if I have my original cornflake box and I identify a square region on that box that is interesting, and then I tilt the cornflake box so that that thing has been affinely transformed, I want to automatically detect the same region in the other image. So what you can do here, there's been a number of different kind of engineering-y approaches that have been proposed for this. Let's see. This approach, what it tries to do is identify what's called an intensity extremum. So if you imagine the image, it's a two-dimensional image, and you imagine the intensity of every pixel as corresponding to something like an elevation or a height, then as you look out over your image, there will basically be peaks and valleys corresponding to bright and dark areas. So what it first tries to do is start from a well-defined peak in that landscape. So if there's one location in the image that is very, very bright, surrounded by relatively dark, it starts there. That's the blue pixel. And then if you imagine climbing to the top of that mountain and taking binoculars and looking in each direction, what you might do is look out in a particular direction and identify a distance away from you where some function is maximized or minimized. So for example, if you're on a mountain and around you is valley, then you might identify the location in this direction where the next mountain is, or where the next peak is. And similarly, if you turn a little bit to the right, you look in this direction and identify where the next peak is. And so on, turning 360 degrees around you. If you do that, then you'll end up with a plot that looks like this, where in this direction I'm on the top of the mountain here, and there's valley, 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 peak, valley, 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 peak, and so on. And this will give you a kind of a blobby-shaped region for each of those. And what that'll do is it'll give you some approximately corresponding regions which you can then rectify after the fact. And you can show that those regions, if you make assumptions about basically that the intensity peaks and valleys don't change from image to image, you can show that these things are affinely invariant. And again, what you're going to do is then rectify these things. So if that's the region as you saw in your first image, and that's the same mountain, valley, peak thing that you saw in your second image, you can then rotate and undo the scalings and rotations of that thing to rectify them. So there are other affinely invariant regions, but oh yeah, this thing. So I'm out of time for that. But oh, come on now. Yeah. So the other ones you can read about after the class. There are invariants to color transformations and intensity transformations. But basically, the bottom line is that in order to use invariants for your features, you need to consider one of two different strategies, which include rectification to undo the transformation, or an invariant feature function that simply calculates something that doesn't change with respect to the transformations. And then you have to think of these two possible scenarios where, in the first case, you want to identify regions in the image that are both interesting and invariant. Or in the latter case, you just simply are just calculating the feature function at every location. Any last minute questions? Okay, my office hours are next.